or this logic diagram, timing diagram. Reset, this one, clock, yeah. Y1 20 okay. And nano 10 100 nanosecond, 200 nanosecond, 300 nanosecond, 400 nanosecond, 500 nanosecond, 600 nanosecond, 700 nanosecond, 800 nanosecond, 900 nanosecond. Reset up to 200 nanosecond 0. Okay, from 200 to continue 1 only. Reset, after reset it will be active 1. Then clock in 100 nanosecond up to 0 only. After that 1 up to 100 to 200 nanosecond 1, 200 to 300 nanosecond 0, 300 to 400 nanosecond 1, 400 to 500 nanosecond, that is this is for clock. 400 to 500 0, 500 to 600 1, 600 to 700 0, 700 to 800 1, 800 to 900 0, and on and so on. And then output here, this is 0, 3, 2, 1. This is for this counter. Down counter. Okay. Sorry. Yeah. Down counter 0 to 1. So 0 to 1 down counter. And then this output 3, from 300 nanosecond to 500 nanosecond. Then 500 nanosecond to 700 nanosecond. And 700 nanosecond to 900 nanosecond. This one will start from here, from here up to this 300 nanosecond same. After triggering up to 500 nanosecond. After that 700. After that 900 nanosecond. So example 4, 2-bit up down counter. State diagram. State diagram S0, state 0, state 1, state 2, state 3. Here clockwise direction. Okay. S0 to S1, S1 to S2, S2 to S3, S3 to S3 again same. Okay. Here reset. This is the reset. Why UPN bar like this. Only UPN like this. So UPN bar, UPN bar, UPN bar. Here S0 to S1, S3, UPN. Here also same. S3 to S2, UPN. S2 to S1, UPN. S1 to S0, UPN. Example 250 up and down counter state diagram. Here S0 to S3, this direction UPN, sorry, UPN. Here S0 to S1. Here this is truth table bar up and down counter. Yeah. In this state diagram, current notation, here S0 to S3 UPN, but S3 to S0 NPN. 7 notation. In 2-bit up and down counter, state table. Here PS percentage rate, NS numerical, UPN bar, NS next state, UPN, Y equal to output. Okay, let S0 equal to 00, S1 equal to 01, S2 equal to 10, S3 equal to 11. Here in present state S0, in NS next state S1, NS S3 output 0. So like this up counter going up. Okay, S0 resets rate only. Here let then here 2-bit up and down counter excitation equations, NS1 equal to PS1 PS0 UPN bar, and then NS0 equal to PS0, Y1 equal to PS1, Y0 equal to PS0. Recall more FS1. That's where clock going to connect with this resistor, reset also, and then X vector, input vector, next state, PS, present state, output vector, feedback, state equations, NS, next state equal to okay, F of S comma PS, X input vector, okay, and then this is H logic, Y vector, F logic, X vector, same is to block this one. And then in logic diagram, then here input shown, input clock and reset, input going to XOR, is the output Y0, Y1. Three-bit arbitrary counter. Example 5, 3-bit arbitrary counter. Design a 3-bit arbitrary counter that will count in the following sequence: 3, 2, 3, 1, 2, 3. If a state is not used, reset it to state 0. If state is not used to reset, it is state 0. How many states do we have? How many registers do we need? How many bits do we need for Y? That is output. Here Also first 3, then 2, then 3, then 1 to 3. Like sequence, we have to design 3-bit arbitrary counter in this manner, in this following sequence. State diagram. State 0, state 1, state 2, state 3, state 4, state 5, state 6, state 7. First reset. Then here Y3. Then state 1, Y2. State 3, 2, Y3. State 3, Y3, Y1. State 4, Y2. State 5, Y0. State 6, state 7. State table assign state values for arbitrary 3-bit counter. Present state, nested state, output S0. Assign state values for S0, 000, 000, S0 always reset state. Okay, reset state. S1 001, S2 010, S3 011, S4 100, S5 101, S6 110, S7 111, 111. So here according to this we need output expectation like this. This is the arbitrary counter. Anyhow 3 2 3 1 2 0 0 0. Okay, then S0 S1 3 get output, S1 S2 output 2, S2 S3 output 3, S3 S4 output 1, S4 S0 output 2, S5 S0 output 0, S6 S0 output is 0, S7 S0 output is 0. Here S0 for S0 here also, and then here also same. Okay. S1 here for S1, then S2 here, S3 here, S4 here, S5, S6 here, S7. Develop truth table. Present state 2, present state 1, present state 0, nested state 2, nested state 0, nested state 1, Y output, Y1 output, Y0 output. For example, PS2 is 0, PS1 0, PS0, PS0 0, NS2 0, NS0 0 0, NS1 1, then Y output is 3, Y1 output 1, Y0 is 1. Then 2-bit arbitrary counter, develop excitation equations, F logic. Here NS2 or NS2 next state 2, PS2, PS1, PS0, PS2 is PS2 dash, and then here also NS1 PS2 dash of PS1 PS0, and then NSO0 equal to PS2 PS0. Develop excitation equations, F logic. Develop the excitation equations for Y. Y1, Y0. So 0 1 0 0 1 0 1 1 1 1 0 1. Here also for Y0 0 0 0 1 1 1 1 0 0 1. So